Hi, welcome back to the breadboard. Today I have an oscilloscope to review. This is a model from RS Pro line from RS Components and is aimed at the educational, small hobbyist, schools, universities, home use and things like that. Now what makes this one special is what comes bundled in the box that you do not have to upgrade at additional costs later on. The oscilloscope is the IDS-2204E, and I have it sitting on the bench here already. I won't bore you with an unboxing video because it's just in a fairly plain brown standard box and your usual foam, so well packed, but I've pulled it out, put it on the bench, and so let's get into having a look at some of the features and things like that. What you can see on here right now is I've been playing with it, decoding some I2C protocol things because I wanted to find out what was happening with a board that I'm developing with a few friends of mine over in Europe, and this seemed like a great opportunity to show off some of its features as well. Anyway, first things first, let's get to the bench, have a closer look at the general view of the oscilloscope, what its built-in features are like. Unlike the oscilloscope that's sitting up here right now, this is the Keysight DSOX1102G. That's a 200 megahertz scope. It says 100 on there, but it's an upgrade feature that came with it to have it at 200 megahertz. But all of the things like protocol decodes and stuff like that, they're all optional extras that you have to buy with additional costs. With this scope, the RS Pro IDS-2204E, they're all included and some. So let's get closer to the scope and we'll go through what the features are and try a few experiments. Now I'm going to break this video or this review up into a number of videos because otherwise it'll end up probably with 2, 3, 4 hours long in total or something. So this first one is going to be looking at basically the features, what the specifications are, general view of the build, how good a display is it, how intuitive is it to use, etc. And then we'll go on to do some experiments and things with it, see how good it is at doing some what I regard as typical hobbyist, educational, or design shop kind of work when you're developing software and you're using it for embedded hardware like IoT devices and things. Quite typically you want to look at the buses that are being used to communicate with peripherals, I2C, SPI, CAN, LIN, RS-232, or at least the TTL equivalents, and a lot of embedded controllers and the like. So this scope has it all. Let's go have a look. So here's the scope in its glory. You're looking at the front panel right now, obviously. Now this is an RS Pro brand. It's a 200 megahertz, 1 gig of samples per second, and it has Visual Persistence Display Technology, VPO, Visual Persistence Oscilloscope. What that really means is that it's got a good display and you can have turn persistence on and off and things like that. That particular feature is fairly common on a lot of oscilloscopes these days. What we're currently looking at here, I just set up a typical use for the oscilloscope, just for the initial view, and we're looking at an I2C bus that we're busy decoding here. So we have a little board here with an analog to digital converter on, an LCD display and things, and it's just polling the ADC through an I2C bus. And as you can see, the oscilloscope here is quite happily decoding that. Now, I'm not going to get into a bunch of details on this right now, just suffice to say it can do it. But what I do want to show you, it's just gone into a screensaver mode there effectively, is a whole bunch of the features that are included in the box. Now if we go over and have a look at the web page on RS Components website, I'm looking at the UK one right now, you can see the price for this scope is £1,300. So that is in US dollars is about 1,700 US dollars. Where I am in Canada, that's about 2,200 or something. If you're really into different currencies though, just for a laugh, it is currently would cost you 0.1 Bitcoin. So if you want to have if you have a bunch of Bitcoins hanging around, 0.1 of one will get you one of these oscilloscopes. From a price perspective, it is very, very competitive compared to other scopes in this price range and feature set. The difference being that you do not have to buy the features to get them enabled. They come right out of the box already enabled. Now if we go down the datasheet for a moment, we've got a few views here. Let's just have a quick look. So we've got the front view, a side view, and here's the back view. So on the back you can see we have a USB port, an Ethernet port, we have a cal port, and we have go no-go output. What are some of the main features of this oscilloscope? Let's just have a look down here. I know a few of them off the top of my head, but let's just go through the data sheet anyway. So we've got a 10 meg depth of memory. So that is when you're capturing data. For instance, I'm capturing this I2C data here. If I told it to do a single shot, I wanted to get into some detail, I can have up to 10 meg of samples captured into memory and then go and review those after the event that triggered it occurred. This allows me to capture some data at that is slowly changing over time, for instance, or something like an I2C or SPI bus where it is rapidly changing data, but maybe it's in little bursts over time and you want to be able to capture a whole bunch of data that would otherwise be quite difficult to do. And that's one of the things I will demonstrate on here a little bit later. Waveform update rate is 120,000 waveforms per second, so more than enough. As you can see here, it's quite happily keeping up with the bus decodes, and I think I'm running that. I'd have to check the frequency, but I think it's about 400 kilohertz. I2C is not a very fast bus. Anyway, we have an 800 by 480 LCD color display, as you can see there. And we have a 1 million point fast Fourier transform capability built in, which we can have a look at a little bit later as well. Various digital filters, segmented waveforms. Now, this is something interesting. A lot of scopes at the entry level do not have things like segmented memory. When you have waveforms that are changing, maybe they're rapid bursts and then not much activity and then rapid bursts, you often, when you're using the trigger, can capture one of those bursts, but the subsequent events may be beyond the range of the captured data because there is not the time to capture it all before you run out of memory, or the capture speed is not fast enough to get the resolution. Your effective sampling rate reduces when you start trying to slow down the overall timescale. So say maybe it's a 2 or 3 seconds worth of events that are happening on something, and they're just little bursts within that, because when you have linear memory, you capture the data for that entire 2 or 3 seconds. That will rapidly fill up your memory. Now if you turn down the sample rate so that you have less samples, what can happen is you start losing the resolution on the signal that you're trying to capture. And I will actually demonstrate that with the I2C bus because it's very, very easy to demonstrate on this scope as well. The segmented memory allows you to compensate for that by having effectively short bursts of rapid capture that are then re-triggered as you go through, and it just populates the memory for the period of the trigger. And then it will wait and reset and then trigger again and wait and reset, trigger again, and fill up subsequent memory locations. So this can seriously compensate for a lot of deficiencies of having just one great big linear memory bus. Now, I do have another oscilloscope here, which is my Tektronix MDO3054. It does not have segmented memory, even though it is significantly more expensive than the RS Pro scope we're looking at today. But it does have the hardware built in to be able to capture the data at a very high data rate for the memory, so it can compensate to a certain extent for the lack of segmented memory, but it still does reach that limit where the sampling rate cannot keep up with the accuracy required for the data rates when you have them just pulsed over a long period of time. Anyway, I digress. What else does come with this? I2C, SPI, UART, CAN bus, and LIN. So these are all probably the most popular protocols that I see people using now. I'm a member of a number of different forums, and we're always talking about connecting an I2C A to D, D to A converter, a SPI based 16-port I/O expander, or a display that works off the SPI bus. The benefit of SPI over I2C, in case you're wondering why I'm mentioning both of them, is that SPI can run at sort of 10 megahertz, whereas I2C runs way slower. It has the UART decoding, so RS-232, different data rates. You can just hook it up to things like the TTL ports coming out of a Raspberry Pi, or an MSP430 or a Arduino Uno or whatever other microcontroller that you want, and you can have a look at the RS-232 data coming out. And then this would also apply to things like RS-422 and 485. The only difference is it's differential, but it's still decodable because it follows this standard RS-232 kind of protocol. You've got network storage function, so when you do screen captures and things like that, you can actually save the data from that screen capture out onto a network drive, for instance a Windows drive. Data logging capability as well. These are all features that are actually built right into the oscilloscope. You also have some software that you can download. Now I got a disk with my scope, I'm assuming that probably comes with all of them, that contains some Windows-based software so that you can connect to the oscilloscope remotely via the USB cable, and you can control it remotely and display data on the screen. And we'll have a quick look at that in a little while as well. You also get drivers for LabVIEW, and I do have examples of LabVIEW. I've already been trying it, and that works very nicely as well. The scope does not have things like LXI, where like a web interface, where you can remotely just take a browser, navigate to the oscilloscope, and display the data. But having LabVIEW for educational and various other things, and even automated testing, is a great feature anyway, because you've got the full SCPI interface protocols that you can interrogate the scope with and everything without having to have that web browser. And that allows you to better integrate it with other systems anyway. So yeah, even the manual talks about the applications being for educational training, laboratory use, QA testing, serial bus design and debugging, and maintenance services and things. And I know that with the oscilloscopes I have in my lab, the predominant use I make of oscilloscopes is looking at protocol decoded waveforms, and also literally decoding them to make sure I'm sending the right things out onto the bus. I actually don't have a completely standalone protocol decoder. You can get them, I just don't have one. And all of my oscilloscopes except for one, which was the original one that I bought, has protocol decoding built in, but the other ones were more expensive scopes. This one, for its price range, to have all these features built in, is a great value for money, I think. So if you're thinking about, we're getting near year end, if you're thinking about what oscilloscopes to buy for a school, for a university, for a small hobby business or something like that, or perhaps you're getting Christmas money and you don't know what to do with it, then you wouldn't go far wrong in giving this IDS-2204E a look. Now, obviously, if you don't need 200 megahertz, then you can go to a lower bandwidth, but you're still going to get all of those protocol decoding features and everything else in here. So let's have a look at the, I'm just going to shut this off and we'll have a look at the back of the oscilloscope a second. Move these things out of the way. Here's the back of the oscilloscope. It actually doesn't weigh much at all. So you can see here now quite clearly. So we've got the USB, the LAN, the CAL, the go-no-go. The go-no-go is an open collector output. So if you're putting it into some kind of controller to signal something or a light, you need to obviously give that a supply. And it's going to have some limitations on how much current you could put through here, as well as the voltages. We have the standard AC input, which will take 50, 60 hertz, 100 to 240 volts. So it's pretty much good for anywhere in the world. It can consume up to about 30 watts. It has a Kensington lock, so you can tie it to the bench so it doesn't get stolen. It also has a big loop here where you could put a security cable through the loop instead to tie it to the bench. There are no boxes, like little cubby holes to put your scope probes in or anything like that. So that's the back of the unit. Like I said, the weight is pretty good. It's got, on the bottom, you've got the bails for tilting it back or having it straight. Rubber feet at the back to stop it sliding around on a bench when you're pushing buttons. So let's just boot this up and you can see what kind of displays we get as it comes up. So all the lights come on. For a change, fully RS Pro branded. It's actually got their logos even in the firmware. So that just took a few seconds to power up, which is pretty good. You know, I've seen a lot of scopes that take way longer to power up and become ready to use. This one was ready in probably what, less than 10 seconds, that's for sure, from powering up. I like the size of the display. It's not touchscreen. We have a lot of buttons all the way around the display for different options. So for instance, if I push utility button, then down the bottom here we've got things like language selection. We have system options, so system information, so it's telling us what the model is, the serial number, what firmware it's currently up to, and URL for more information, www.rspro.com. SPC, signal path compensation. This is a calibration that you can do. It will take about 10 minutes to run, so I'm not going to do that right now. You can erase memory. I'm not going to do that either, because I've just got this set up for a few things. But if you needed to completely erase the memory from waveforms and various other things, maybe you're going to lend this scope to somewhere else and you've got some proprietary waveforms that have been captured, then you can do an easy erase of the entire scope, set it back to factory conditions effectively. You've also got self-calibration, function modules. So this will tell you what is already included. So we have the serial bus decoding, we've got search trigger settings, segmented acquiring, and some demo modes. It says FFT with dual display is not installed, so that must be a software upgrade potentially that you can get for the oscilloscope. It's not included in here. So we go back from there. Probe compensation, this will control what frequency comes out of this test probe pin here, which allows you to set up the oscilloscope probes. If I just plug these in a second, so if I take one of these channels, let's just take channel 1, put it on the probe compensation pin. Alright, so they're both set to 1 volt per division. Fit to the screen, and there we go. Now we've got a little bit of noise, which is probably being picked up because of some of the devices I've got around in the lab here. Probe compensation, in case you didn't know, is how you adjust your oscilloscope probes to properly work with your oscilloscope. So you can see here that these waveforms, let me just expand this out a little bit just to make it better. You can see that they're fairly square on the top and the bottom of the waveforms, which is what you want to have. Now I can mess this up. Let me just grab a screwdriver. I probably shouldn't be using a metal one, but so if I on channel 2 just tweak this around, you can see sometimes you'll get an oscilloscope and the probes, I'm going to do both of them, it doesn't take a moment to change it. All right, they could arrive at your door and you could see waveforms like this. This is completely incorrect, and all you have to do is clip it onto the probe compensation pin with the oscilloscope probe, and usually you do this in 10 times mode. These probes are fixed as 10 times probes, so you need to make sure that even in your oscilloscope setup you also set it to 10 times for the probes, and you just tweak the screwdriver to get them flat on the top and bottom and minimal overshoot on the leading edge and trailing edge. So let's just do the channel 1 again, put it back. You can see you go too far, you get some overshoot and it comes back down, undershoot, and just level it off. Okay, and there you go. Now, what you can also do, which will probably get rid of some of this noise, if you go to channel 1, we're set to times 10, but the bandwidth is set to full. Well, one of the nice features of a lot of scopes is you can reduce the bandwidth. This oscilloscope by default is 200 megahertz, but you can effectively reduce it to 100 megahertz oscilloscope, or put a filter in to take it all the way down to 20 megahertz. This is great for doing analysis of power supplies and things like that, because they're normally limited to 20 megahertz as being the upper limit for noise emissions from a power supply when you're doing noise checks and things like that on power systems. So what are some of the other features of the oscilloscope? Obviously 4 channels. You've got your 1 gigasamples per second. You would get that usually if you're using just channel 1 and 3. If you're using channel 1 and 2, or channel 3 and channel 4 together, usually that will halve because of the nature of the ADCs. This is typical of pretty much every oscilloscope I've come across in modern times. We've got measurement capabilities. So you've got your standard variable select and adjust, pick menus and things, dials, but we've got a measure capability where we can add measurements. This is fairly typical of all scopes, but let's have a look at what kind of things we can do here. So we can measure all of these different things. So you got peak to peak, max, min, amplitude, high value, low value, mean, cycle mean, RMS, area, a whole bunch of them. These are all detailed in the manual, and I will provide a link to the manual. You've got statistics, mean, standard deviation, etc. And you can set some reference levels as well. I'm not going to set any of these up right now, just going through. You can see they're already actually doing some on the calibration signal. Cursor, so again fairly typical. You can slide your cursors to do measurements. It tells you the distance. There's 2 cursors here, and it will tell you the distance between the cursor 1, which is this blue line, and cursor 2, which is currently showing us as 1 millisecond. You're selecting the horizontal cursor. So now I'm moving one of them. I've locked the other one in place. So I've moved that to there, for instance. So I can pick the other cursor, move that, or I can lock them both together. The unit of measurement we're doing, you can change that to be the frequency measured between those 2 cursor points, the duty period, any phase shifts, etc. So deltas, and phase. So that's pretty cool. That's cursors, and I think you can turn on horizontal and vertical cursors. Again, base unit, so you've got lots of capabilities with the cursors. We've got display capability. Oh, let me turn the cursors off. Oh, there we go. Just got to push the button twice. Applications. So this is where you can select some of the built-in capabilities. So we've got the go to no-go testing. So if we select that application, press it again to confirm, it's going to now start putting in and figuring out some go no-go. Right, so I'm not going to go into all of these. I'm going to do a few separate videos for each, certain unique features that might need a little bit of clarification. Built-in DVM, so let's go across one and we'll select that. So now we have the DVM down here. Some of the go-no-go displays look like they're still just showing. So we turn the DVM on, we're measuring channel 1. This is measuring the DC, so this is 2 volts peak to peak, but it's centered around 0. So it's telling us it's 1 volt. Mode, we can change that to be AC RMS, which is still going to be around about 1 volt, not quite. DC, duty cycle, that's 50%, which is correct. The frequency, which is exactly 1.0000 kilohertz. And we've got AC RMS. So we covered all of those. So you can see it's only a 3-digit DVM, but this is actually independent of the oscilloscope, like the normal ADC. So it's not a 256-bit only resolution oscilloscope DVM. It actually does a separate measurement. So let's go back, and the next one is data logging. So we'll just go have a quick look at that. So these are, remember, all of these are built in to this as standard. So DVM still turned on, so you can see you can run multiple of these apps. To turn data logging off, you can set it up to log images or waveforms. So waveform memory or image, just take a snapshot of the screen and the interval of what you want to log. So this is one of the features that they mentioned in the brochure that basically says you can capture images over a long, so you could leave this running for a couple of days, and every 5 seconds you can have it capture an image and save it to a USB stick or remote drive if you set that up or something like that. And this waveform, I think, is sending the waveform data. File utilities allow you to set up where you're going to send this to. File utilities, sorry. So you create a folder, rename a folder, fairly standard oscilloscope file utilities. The last one, which I haven't had a chance to play with yet, is a digital filter. So what this allows us to do is you can turn on a filter and off. You can select whether it's a high pass, a low pass, or a band pass. Right now this is set to low pass, so let's just leave it there for the moment. Then you can pick your frequency. So low pass means that anything below a certain frequency is going to go through. Now right now this is set for 50 megahertz. I'm going to try and get this down to something that's going to actually impact these square waves that we're measuring right now. So it's a 1 kilohertz square wave. So now we're at 10 kilohertz. Now even at 10 kilohertz, if I just clear the display here, so what you can see here now, we've put a digital filter on that square wave, and it's actually now rounded off because we've only given it a 10 kilohertz filter. So 1 kilohertz is a nice square wave, 10 kilohertz is not enough to be able to maintain this. So if we actually go back a little bit just for fun, and we'll go back into the app, the filter, and we'll change the limit now. So we're at 10 kilohertz. If we change it down to 1 kilohertz, we're probably going to turn it into a sine wave, because it's not going to allow the harmonics which are required to turn it into, there we go, and that's our square wave. Now we put a digital filter in. Now that's actually quite a handy feature that I haven't seen on other oscilloscopes, the ability to have this digital filter sitting there. So that's excellent. Okay, so what else have we got? It had saved those waveforms as reference waveforms. That's why I couldn't get rid of them. I just suddenly realized what it was from. Let's turn the DVM off just to clear it out of the way. We'll turn that off. Now if we go to acquire mode, what you can see here for acquire menus, sample, peak detect, average, and you can change the number of samples from 2 up to 256. You can turn your record length, 1 megapoint, 100K, 10K, and a 1K points for sampling. So you've got XY mode, on or off. You've got, just reset horizontal position to 0. Sample mode, sample, peak detect, averaging. Ability to change your record length. And the other bit here is where you get the segmented memory from. So we can turn segmented memory on, and we can run the segmented memory, which is putting it into buffers. By default, I think we've got 10 segmented memories, but you can actually change that. Intensity, so you can change the waveform intensity, the graticule intensity, the backlight, auto dim after 60 minutes. And you've got graticule, which we were looking at before. Let's just get out of there. A help menu. So you can actually go through all of the different features. This is another thing that makes it great for education, is that you've got a built-in help capability right here on the screen. We've got save and recall, which allows you to save waveforms, images, save setups, recall waveforms, recall setups, and you can edit the file labels. This is very handy if you're using a USB stick and you want to be able to have a setup for some protocol decoding, maybe looking at specific analog signals or something like that. And then you've got your utility menu, which we looked at the beginning. Set your probe frequency. So there's probe compensation down here. You can change the frequency of that. 10 kilohertz. What can I go up to? 200 kilohertz. That's pretty good. All the way down to 1 kilohertz. We can set the whole oscilloscope back to defaults. Probe compensation, yeah, that's all for that one. I/O, so USB port. You can select it to be a computer. This is the port here. Or you can select it for, no, it's the back one, I think, to be a printer. So you could send data to a printer. You can get the Ethernet details. You can tell it to use DHCP or BootP. I'm currently using DHCP. BootP is the same thing. If you're not using DHCP, it means you need to configure the IP address, gateway, and all that kind of thing yourself. And then you can just save it. For the socket server, this allows you to turn on the socket server that things like LabVIEW can connect to. You can select your port and you can turn it on or off. The IP address will be the one that you set with the previous menu. And that's all of that one. File utilities, hard copy, printing or saving. So when you hit hard copy, there's a dedicated button up here for it. You can ink saver, doesn't print the background. File format, PNG or BMPs. Function is either to print or to save it to the storage. Ability. What we haven't looked at now, you've got search capabilities. We'll go through these. This allows you to have an extended waveform and then, or a protocol, and then actually go through and search for different characteristics within the data and things. You can play through the segmented memory one by one automatically. We've got the channel settings for each of these, including the probe attenuation. Now we're on ×10. If you do a factory reset and things, it'll go back to ×1 by default. So you have to then reset it back to ×10, so just be aware of that. Change the bandwidth. You've got the input coupling, AC/DC ground. You can invert the input. So if you're going to do a differential probe, you can invert one input and add them together, and there you go. You can set your probe to be current or voltage. All right, so if you had a current probe plugged in, or if you're measuring, say, the voltage across a known resistor so that you can measure the current, maybe it's a 100 milliamp resistor or something, you could set it up to display the milliamps or amps or whatever. So that's a handy feature. What else is on here? I think that's pretty much everything on that menu. So math menu. So we've got standard math, which is channel 1 for the source, 4 channels, 4 reference signals. Fast Fourier transform is what you might call, so after fast Fourier transform we have advanced math. So we looked at the basic math here, which just gave us plus, minus, times, divide. With advanced math, it's defaulting to something here because it's got a little waveform there. You can pick, I don't know if I turn off, yeah, got to leave it on. You can pick a waveform, so in this case channel 1, and go back to math, sorry, we're on the wrong one. So we can edit the expression, and right now it's just channel 1 plus channel 2. I got nothing in channel 2, let's just turn that on as well. Both set to 1 volt per division. Go back to math. And advanced math, so you've got channel 1 plus channel 2, and that is showing us, we've got this now 2 volts per division. So these are 1 volt and 1 volt. This is showing 2, and you can see it's basically the same height as these, which means it's twice the value. But we can edit the expression. Right now we've got channel 1 plus channel 2. Let's backspace that out. We can pick channel 1 through channel 4, ref 1 through ref 4, and then we can do things like integration, differentiation, log, linear, exponents, square root, absolute, radians, degrees, sine, cosine, a whole bunch of different maths, and you could build up your own mathematical function and apply it to your signal. Now, I've never used this before, so I'm not going to try and demonstrate it right now, but you can see here, this again is all built in, which is kind of cool. I don't know if we've got anything else on the math. Nope, that's pretty much it. So you have FFT, math, advanced math, that's on that menu. So the other menus are things like standard trigger, single trace, auto set, run and stop, going back to default setup. And as I said, if you do default, it can change. See, it just did that. So there was no warning. I just hit default menu and it changed my probe from a ×10 now to a ×1. So you can actually twiddle the dial up to ×1000 if you want to, or you got a quick set for ×10, which is nice. And channel 2 will be the same, to reset that to ×10. Notice that it doesn't change the display. What it does do is it changes the scale. So you can see here we've got 1 volt per division on here and here. If I turn it back to 1, right, now it's reading 100 millivolts per division. So it's changing, when you change the scale, it's changing the millivolts per division on you, rather than shrinking the signal and you know, rather than increasing it and having you have a smaller signal. So it knows you've got a 10 times probe there, and that it needs to adjust this. Now, the concern I have is one of the selling features of this oscilloscope is it will go down to 1 millivolt per division, and it will. But if I crank this down, sorry, going the wrong way, I can only go down to 10 millivolts per division. That's on channel 1. Let's just go back to channel 1. If I set my probe to ×1, then I've got my 1 millivolts per division. But what's happened here is I am actually, let me just put these on ground so we can, right, it's got a lot of noise there. It's fairly typical on this level of resolution. So you got 10 millivolts per division. We change that to ×1. Now you've got your 1 millivolts. But these probes are they're 10 times probes. You cannot switch them to ×1. Right? They're fixed at ×10. So it means that with the standard probes that come with this, you can't do your 1 millivolt per division. Not with a 10 megohm ×10 probe. You would have to put in a direct coaxial connection and have the 1 megohm input impedance, or use some alternate probes that have a switchable 1 meg, 10 meg input impedance. Now, really, you very rarely want to use 1 megohm input impedance when you're measuring signals anyway, because a 1 megohm load on most analog and digital signals now is actually getting quite significant, especially on analog op amps for feedback and voltage dividers and things like that. It will mess you up. So yeah, using a ×10 and being restricted most of the time to 10 millivolts per division is more than enough. So I'll just put these both back to ×10 and get our signal level back to something. You can see the noise that's in here. It'd be very interesting to try and figure out what in my room is generating that, because if I actually ground this internally, you know, it's still there. Which one am I on here? Channel 1, ground. See, it's not being generated inside because this ground is actually on the front end that is doing the grounding. But I do have this intermittent little bursts. It could be the switching power supplies in my lighting. It could be the Wi-Fi. I've got my laptop right next to the oscilloscope. It could be interference from this thing. Actually, let's just try taking that off, and oh, well, I guess it is. So you can see it's actually interference from this MSP 430. It's not a 430, but it's an MSP launch pad So it's actually noise coming from that, because the grounds of the oscilloscope, there we go, I had the grounds still connected to this. Now that I've disconnected them, you can see the noise has gone away, which is really nice. So if I crank these back down to 10 millivolts, I mean that's fairly typical noise levels for this kind of thing. These cables make great antennas for picking up noise. So even though I've got them grounded at this end, there's still these loops to pick up noise and everything else. Even if I take it off of that ground, which should be a fairly good ground. Right, so actually it's picking it up from itself. Interesting. Just play with this one probe a second. Yeah, must be some ground-based interference when I take this off. This is chassis ground, which is, you know, these are also chassis ground, but the probe itself was connected there. That probably had a little bit of a picking up some interference. You can see as I move the scope probe even close to the oscilloscope. All right, it's picking up. This is basically the principle of a EMI probe too. It's a little more sophisticated, obviously, but that's making a little loop that can pick up RF. And I can put, I know the power supply is on the back of this oscilloscope. You can see it picking up noise from that. Going near this, you can see that noise coming back in again. That burst is actually the update interval for the LCD display on this little thing down here. This is kind of interesting. Anyway, I'm digressing again. I think that pretty much covers the intro to the RS Pro Digital Storage Oscilloscope. A quick run through all of the features. I'm probably going to have to edit this down a little bit, but I will make some more videos where we will just simply focus on using I2C, using SPI, you know, RS-232 decoding, things like that, and trying out some of the other features. Maybe we'll check out how accurate the DMM is and stuff. We'll also do maybe some bandwidth checks. I have a 120 megahertz capable waveform generator, so we'll see. I don't have something that will generate waveforms above that, not as a controllable signal anyway. See how well it does. But anyway, that's it for now, so we'll see you soon on the next video.